Last time we talked about this class, and actually there is an example of this in your script for a field. So if we go look at field real quick, you can see that it has basically this instance. So it's like um, everything that is commutative. Sorry, let me say it this way. Anything that's commutative and a group is abelian. So you can just create an instance for everything like this, and fields do this. So it would be cool if that existed for abelian as well. Anyway, so you can literally write instance. So that's the name. Okay, so then you just write commutative a group a abelian prime. Whoa. A, I think. Yep. So alternate implementation for abelian with a single instance for every type. This is modeled after field, for example. So we want to grab from here to here, grab a permalink, and we'll put that permalink in there. Cool. There we go. There's Billion. Hey, Gil. How's it going? And the rest of chat, whoever may be here. So, yeah, I looked this, or I asked the PureScript people about this, and Harry responded. Harry's super nice. And so that's what we get. There is actually an example of this exact type class. Well, not this exact one, but a similar thing for field. All right, so semi-ring. A semi-ring is an algebraic structure with a set R and two binary operators, plus and dot, called addition and multiplication. Hey, kitty. You hear Layla? Hi. Okay, so R plus is a commutative monoid with identity of 0. So A plus B plus, yeah, so it's associative, it has an identity, and it's commutative. Okay. Next, the laws for monoid and multiplication. Then the laws for multiplicative distribution across addition on the left and right. Mm-hmm. And finally, the law for multiplication with 0 that annihilates R. So this is just, this has a name, doesn't it? This is just this last one. What was it called? A group? Doesn't this make it a group? I think. Okay. Anyway, I noticed that addition must be commutative, but multiplication does not. This may seem odd at first, since the multiplication we know is commutative, but you have to keep in mind that addition, multiplication, and abstract operations, and 0 and 1, are abstract operations, and 0 and 1 are abstract members of the set R. In the concrete case of numbers, they're the operations we grew up with, and 0 and 1 are actual numbers, but in the abstract sense, 0 and 1 are just additive and multiplicative identities. Okay. So we have add, 0, multiply, and 1. Uh-huh. So if we had an int, we just have int add and int mul, and then 0 and 1. Okay, so there's the semi-ring for integers. And apparently we're not using, or we're using uh, JavaScript's addition and multiplication operator in this case. Okay. For unit, everything is unit. Fun. All right, semi-ring for functions. Interesting. Okay, so if you have a semi-ring B and a semi-ring A to B, we can add these two things together. So what's F? It's got to be some function. So you apply F and G to some X. It's kind of weird to see the X there, isn't it? A to A to A. Oh, well, okay. It's equivalent to writing this X on the other side, I suppose. So it's fine. Okay, so anyway, this is a bit complicated and confusing, so let's break it down. Here, um, instances for functions of type A to B, where B is also a semi-ring. Yep. But looking at this, we may ask, what about functions with multiple parameters? Well, remember, thanks to currying, all functions technically only have one parameter. They instead return a function to support multiple parameters. So B here could be a function. We can best see this by replacing B with B to C to D. Yeah, so it looks a bit strange, but I'm pretty sure that it's just that this X could just be a lambda on the other side. Yeah. All right, so next one. The identity for add is 0. Yeah, because it's just the 0 from the right-hand side. So it's B's 0. Yeah, they're different zeros. Same is true for 1. You could also just replace this with const, I suppose. All right, so semi-ring laws for functions. You can verify the laws of our semi-ring instance. Here they are again. So we have associativity, we have this identity law, and this commutative law. One thing I'd like to look up at the end of this is to see if there's a property testing library for PureScript that does these kinds of tests for you. That exists in Haskell, so I just kind of assume it exists. All right, so given B is a semi-ring, we have add H0. So we take HX and 0x, replace the 0 with its definition. So this is the 0 for B. And then we have the same x to hx, which is equivalent to h. Sure. I'm okay with this. Sorry. Proving the other laws are something that we programmers must do. Oh, okay. Sorry. I completely misread that sentence and it blew my mind. Okay. A ring adds one more requirement to semi-ring. In a ring, the set has an additive inverse. Oh, is this the group? Ah, yeah, okay. So the annihilation thing is not a group because that's not an inverse. Um, I misinterpreted this annihilation piece as being an inverse. So this this chapter is on abstract algebra, so they're just going over rings and groups at the moment. So I guess it's really more just like group theory. How's it going, Jabby? How are you? So anyway, this is the commutative group. So a ring is a commutative group, and a semi-ring is a commutative monoid. Mm-hmm. Okay, so the ring adds this one thing. Great. And for integers, we can just have int sub. Okay. For unit, it's just unit again. And then here's that thing for function, which is exactly the same as the addition and subtraction. A group has this. So there's a way for you to invert the thing. So let's pretend we have an integer, like wrapped in a new type because it's easier, and it has a semigroup instance and it has a monoid instance. It can be a group if there exists a function turning that thing into the other thing and then multiplying them together is the monoid value, or like in this case, plussing, right? Because we're doing the addition monoid. So there needs to exist a function. We're given any a, and then the g inverse of a. You end up with the monoid mempty or the 0 or whatever you want to call it. So those are the two pieces you need to be a group. Mm-hmm. And they must commute, right? Like it needs to be commutative. Yes, exactly. Monoid exists in the hierarchy, so like it would be it's semi-group at the top, then monoid, then group, then abelian. I think there may be some other stuff in between there that like I'm unfamiliar with, but this is the hierarchy that's in PureScript today, as far as I know. I don't know that it has changed. Um, okay, so where were we? We were talking about rings. So here's the ring of function, and it looks exactly like add. Cool. So commutative ring type class. All right, so rings are commutative for addition. Commutative rings are commutative for addition and multiplication. The type class is very simple since we cannot enforce commutativity in PureScript. So, yeah, it's just like given a ring, you could have a commutative ring. Yeah, and we just have like these basic instances. Yeah. So again, like you have to prove these things. They don't actually give you anything. Like in this, they don't give you any tools until maybe for a commutative ring, you can do something simpler than you could for a ring because there's, I don't know, some fancy math that you could apply. All right, so a Euclidean ring, as far as I know, nobody has come up with a non-commutative addition yet. Yeah, exactly. So, Jappy, the one thing I mentioned a bit earlier is I want to see if we can find a library that would test all of these things for us, similar to quick check checkers. Is that what it's called? I think that's what it's called in Haskell. Okay, so a Euclidean ring is a commutative ring with one more requirement. Euclidean rings support division. Blah. There's some pretty involved laws, but we won't go into them here. Okay. Yep, here we go. So this is the reverse. Uh, you start with a magma, which actually you don't describe in PureScript because there's no way to test this, I guess. Like it would be tough to test this, I think. But it's a binary operator that's closed under a set. Yeah, and then semigroup, monoid group, abelian group. Cool. All right, and then bottom to top you have okay, division with remainder. This is important, not division as in rational numbers, but division with remainder. Okay, that's good to know. Actually, let's look at Euclidean ring. Data Euclidean ring. Oh wait, this is the JavaScript. Here it is. Yep, so it's just div mod. I don't know what degree is. What's degree? For all non-zero a, degree is greater than or equal to 0. I don't. Okay. I don't know what this int degree thing is doing or what its purpose is offhand, but okay. There you go, Euclidean ring. All right, so anyway, we got R with multiply is a monoid. R, some set R, I guess, with plus is commutative. And then the ring adds subtraction, and the R plus is a group, so it can be inversed. And then a commutative ring is how it's cold outside. It's freezing outside right now. All right, so there's chapter 8, and I think I want to just go look at I'm gonna go see if there's a quick check library for this stuff. Um, quick check pure script. Let's see what that brings up. Okay, so here's pure script quick check. There's a guide. Let's see if it does any properties. Or sorry, if it does any like laws. All right, so arbitraries. Cool. Okay, so first functor law. No, this is like us defining this. Um, pure script, quick check, checkers. That's what it's called, right? Um, okay. Quick check laws. There we go. Okay, cool. So there seems to exist a laws pure script quick check laws which you could use to test a whole bunch of stuff. So very cool. Um, I'm not gonna test one of these. I guess we could, but uh, anyway, it's good to know that it's here. So I'm gonna put this as like a reference for myself. Um, so could use a combination of to test various abstract algebra properties or types. And then we should have, actually, we could probably just do this, right? Yeah. And then also this, I guess, should work. Okay, cool. So this, neat. Maybe we'll do some of that in the next like partial chapter. I'm not sure.